So I'll be talking about power analysis, and you might be wondering, why should you even bother with this extra analysis? And it's actually really important when you're designing your study, because if somebody came up to you and said, look, the study you've planned, there's no hope of you detecting the effect you'd like to see. Now, if somebody told you that, would you still continue your study? Probably not, because you're going to be wasting your money and wasting your time. And that's what the power analysis does for you. It can answer the question, how many subjects do you need for your study? Or often you collect multiple runs per subject, and it can also answer how many runs per subject you need in order to detect the effect that you like to see for your task. If that's not enough for you, if you ever apply for a grant, the grant reviewers are more and more starting to request power calculations for fMRI research. So if you want to make your grant reviewers happy, you should do a power analysis. And I think people are often surprised when they do go to do their power analysis, because the sample sizes are typically much higher than what they thought they needed. So, and of course, the grant people are interested because they don't want to waste money collecting data that aren't going to show anything, and they also don't want you to collect too much data, which is also another way of wasting money. So what I found interesting when I entered the field of fMRI, prior to that, I worked with some people doing medical research. And a lot of my time was spent analyzing their data, but a couple times a year, I had to sit down and do tons and tons of power calculations when it came around to grant writing time. So then I moved to fMRI, and I realized nobody was doing power calculations. I found this very shocking, because it was such a big part of the grant application process in the other field I had previously been in. So the research is rather recent in this field, and part of the reason people weren't doing it is because the data are really complicated. As we know, we have this mass univariate approach. We have all these voxels that we have to analyze. And the model that we use to analyze the time series for each voxel, it's not a very simple model. It's a mixed effects model. The variance structure is rather complicated. So what did people do if they weren't doing power analyses? Well, they would say, well, last time I did a similar study, I had 8 subjects, so I'm going to collect 8 subjects again. Then there are these weird rules of thumb. Like, I think it used to be 8 subjects when I started fMRI, like 8 subjects is enough. And then it's increasing. I think it's up to about 16 subjects now. And you can't really have a rule of thumb, because everybody's design is different, and the strength of the activation and the variability will be different. And the most disappointing thing is when I was doing my research, and I was really excited about it, and I was talking to a graduate student in the psychology department, and I'm like, I've created a power calculation technique. And he's like, I don't care. And I was like, oh. And he's like, I just keep collecting data until I see what I want to see. It's like, oh, who's paying for that for you? So, these are the things that people used to do. But back in 2002, there's a paper by Desmond and Glover, and they were really the first to look at the mixed model for fMRI data, to pick apart the mixed model. And 2 of the components in the mixed model that make this tricky is you have 2 variance components, a between subject variance and a within subject variance. And they went through and they estimated these parameters, and they studied power under different situations. One thing that was a little weird about their not weird, but what they did do was they used a block design study. And instead of using the traditional model that we use, which is a boxcar convolved with a hemodynamic response function, they separated their data into time points during task and time points during baseline, and they did a 2-sample t-test, which is roughly equivalent, but it just meant that their approach was really only applicable to block design studies. So a great thing about this work is that it at least communicated to people, look, if I have, and the way this graph works is we have power on the y-axis, and this is the number of subjects, and these are the number of time points in each block for this block design study. And you could look at this and say, well, look, if you only have 25 time points for each block, but I have 100 time points for each block, there's almost a 2-fold, well, not quite, this is about 50% power, and this is about 80% power, which is generally accepted as a decent level of power, there's quite a difference in the power of those two studies. So power calculations are important for your studies. So they're definitely on the right track, but unfortunately people would then look at their variety of graphs in their papers and be like, Desmond and Glover said I needed 20 subjects, so I used 20 subjects, but completely different designs, and who knows how the variances compared between their analysis and the variances in their approach. But people were at least trying, so give them credit for that. So recently there have been quite a few papers about doing power calculation for fMRI, and so now there are tools out there that are general and can be applied, and you can basically, part of the thing with power analysis is you need to match your power analysis model to the analysis you're actually going to do. And since there are all these options now, it's easier to do that. So I'm going to go over each of these. And the first is the one I developed, which is similar to the Desmond and Glover approach, except the model, you can use any type of study design. It's not only block design, you can have event-related design. And I also included a temporal autocorrelation structure, which I'll talk about briefly later. And that's a region of interest-based power calculation. Then the next approach is a random field-based power calculation, which allows you to look at power on the brain, so you can get maps of power. And they're corrected for multiple comparison issues that come up in fMRI data. And then there's a false discovery rate approach, which is similar to the random field approach, except it's controlling false discovery rate. And that's a newer method that was recently introduced. And a new direction that I'm going in is looking at this use of something called internal pilot studies. And what those are is it's kind of, as I said before, when you do a power analysis, you'll see that there are parameters, and you have to, ultimately you're guessing what these parameters will be in your data, and you're calculating power based on these educated guesses. Sometimes you guess wrong about what your variance is. So the idea of the internal pilot studies is that you do your initial power calculation, you collect, say, half of the sample size that you were told you needed, and you then use that pilot data to re-estimate the variance only, and you update your power calculation. And then finish your study, and then you reuse the pilot data as well as the new data to do your final analysis. So sort of a way of getting a more accurate power calculation. Okay, I'm just going to quickly define power. So the definition of power is the probability of rejecting the null hypothesis when the alternative is true. So the first thing you need to do when you want to do a power analysis is you need to specify your null distribution. So you can see this distribution is centered at 0, because typically our null hypothesis is to test whether a parameter is equal to 0 or not. And this distribution also has some variance associated with it. It's important for the power analysis that we know what that variance is. The next step is to specify the effect size, which I'm denoting by delta, that you would like to detect in your study. And then once you have delta, if you scale delta by sigma, this gives you the mean of your alternative distribution. At least I'm assuming normality here, but it's similar for if you're using t-distributions. Anyway, so once you have these two pieces of information, the last piece you need is your false positive rate alpha. So this is just whatever threshold you're using or you're planning on using in your future study to determine whether a statistic is significant or not. You find what that threshold is. So here's the threshold. The upper tail region under the null distribution is equal to alpha. And so this is now telling you that to the right of this line is where you would reject the null hypothesis. So then the probability of rejecting the null when the alternative is true would just be the area under the red distribution to the right of that line. So that's all that power is. Generally, it's a pretty simple calculation. And there are basically 4 pieces of information that you need for it. The first is the number of subjects that you want to use in your study. And this is typically what you want to fluctuate until you hit that 80% power or 90% power that you're interested in attaining. And then there's the size of the test you'd like to use. Commonly we use 0.05. The size of the effect you're interested in detecting. With fMRI data, I think there's more intuition for this, because people are pretty good about reporting percent signal changes, so you can kind of read in the literature kind of the size of the effect. The variance, on the other hand, people don't really report variances. So we generally have very little intuition about variances, but we can estimate variances from pilot data or from similar studies. So these are the 4 things we need. And when I go through each of the methods that I described, I'll be adding things or expanding on some of these 4 things, but they all basically use these 4 ingredients. So I'm going to start with the ROI-based power calculation. It's really flexible. What's nice about it is that by focusing on a single ROI, I can then spend more energy focusing on other things. And that allows me to not only change the number of subjects and look at how that impacts power, but I can also alter the number of runs per subject and see how that impacts power, as well as the length of the run, or how much time each, or how many blocks you have in a block design, or how many trials you have in event-related design. Okay, so here are our four things that we need, and the only difference is now instead of only having the number of subjects, N, I can also include numbers of runs and numbers of trials. So I'm making it more flexible. But if I want to do that, that means that I have to be more careful about my variance that I'm using. And you have to sort of pick it apart into all of the pieces that exist when you run a mixed model. And here's, it doesn't matter. Anyway, so here's just a breakdown of what these variance components are. So first, if we just focus on a single subject and we analyze, so this is a single run of data, so we're taking snapshots of the brain over time. Now, if we pick a single voxel out of that brain and look at the time series in that voxel, we'll find that the covariance of that time series isn't, it's kind of complicated. It has both this within subject variance component, which is expected, but there's also a temporal autocorrelation component that's there. So far, this is one parameter, and this correlation is usually can be parameterized with 2 to 3 parameters. Sometimes it can have up to 10. So far we have 3 variance parameters, 3 or 4. But we don't just have one subject, we have multiple subjects. And this introduces a second variability, the between subject variability. So now we have 5 parameters. So instead of just a single variance component, I have to estimate all of these things if I want to have the flexibility in the power calculation. Okay, so here's an example of the types of power curves you can get out of this method. This is from a block design study. It was I forget what the data were that I based my estimates on. It was one of those imaging analysis contest data sets from the Human Brain Mapping Conference. And the subjects were read sentences from the 3 Little Pigs or something like that. So it's an auditory task. But anyway, so here we have power on the y-axis. And on the x-axis, we have the number of cycles. It was a block design. So it was a 30-second cycle. And I just put the corresponding time in minutes up here. So each of these power curves is for a different sample size. And the reason they end at different points is because I capped how much money you could spend on the study. So gives you an idea of the cost and your limitations in power by cost. So there are a couple of things to notice. The first thing to notice is that another thing people often do is say, I'm just going to leave the subject in the scanner as long as I can. But you can see here with the 17 subject data, if you look between 15 and about 25 cycles, so it's about 8 to 14 minus 8, 6 minutes that you're keeping the subject in the scanner, and you're really not getting much payback, right? you're just boring your subject. And the quality of that data is probably not that great. And that happens with all these things, diminishing returns. So the other thing you can notice is there are multiple ways to get 80% power. And so what's interesting is we can look at each of these combinations where we hit 80% power and we can calculate the cost for that study. And that's what this is. So just focusing on cost to achieve 80% power, where cost is calculated as $300 per subject plus $10 for each extra minute. So this is assuming basically $10 per minute, and it takes you 30 minutes to just do all the initial stuff you have to do when you're scanning someone. So this first graph is illustrating time in minutes as a function of the number of subjects. And of course, if you have very few subjects, you have to scan each subject longer in order to get your power up to 80%. As opposed to having a lot of subjects, you can scan them for a shorter amount of time. What's interesting is that if we then look at cost, which is the y-axis here is a function of number of subjects, it's not necessarily true that the study with the most or the least number of subjects is the cheapest. Those are actually the more expensive studies. And the cheapest study ends up being around 20 subjects here. And what happens is, in this case, the cost is being driven by how long they're staying in the scanner. And in this case, with 22 subjects, the cost is being driven by this baseline $300 per subject. So yeah, power calculations can be really useful. As I said, you could also look at numbers of runs. So in this case, this is for an event-related design. I fixed the design is the same for everybody. The study paradigm is the same. It's the same length for everybody. And I'm just looking at power as a function of numbers of subjects, and also we have differing numbers of runs. So again, you can see diminishing returns. With going from 1 run to 2 runs, there's a huge, a pretty big increase in power by adding that second run. But from 2 to 3 runs, the difference is pretty minimal, and from 3 to 4 runs, you're kind of wasting your money at that point. So I also looked at this power as a function of cost, and again, you can see the white and the blue lines correspond to the 1 and the 4 run studies, and those tend to be the most expensive. And then and cost was calculated the same here as it was before. And then the 2 and 3 run studies have comparable costs. But if you think about it, I'd probably go with the 2 run study, because then you can spend that 3rd run collecting data on some other task, or perhaps some resting state data, or DTI, or something else. So you can better use the time you have in the scanner. Okay, so that's all I'm going to say about the ROI-based approach. And of course, often when people see that, they're like, oh, but I want to control for multiple comparisons and have whole brain maps. And that's what this random field approach does. So this approach was developed by Satoru Hayasaka. And the way random field works, random field theory, if you're not familiar with it, it uses this maximum statistic. And the idea is to control the probability of having any false positives, which is known as the family-wise error rate. And it allows you to threshold the whole brain images and control for multiple comparisons at the same time. So the power calculation uses a non-central random field distribution in order to calculate power. Okay, so back to our 4 things. We still need number of subjects, type 1 error rate, size effect, and the variance. But now we also need all the parameters associated with random field theory maximum statistic. And basically that boils down to knowing the Russells, which is a resolution element, and the degrees of freedom. I'll talk more about that in a second. So basically here's how the approach works. Under the null hypothesis, you assume a central random field theory. So this is the same as that null distribution I had before. And then for the alternative hypothesis, You have to pick the regions in the brain where you believe the activity will be, and you assume a non-central random field for those regions. So back to the requirements. We need the non-central max random field theory statistic, and that requires a thing called the RESL, or the resolution element count. And this is just the volume of the search region in units of smoothness of the data. And the other thing you need is RESL density, and this is a function of the degrees of freedom and the statistic threshold associated with the type 1 error rate of alpha. And I'm going to talk more about the degrees of freedom here. So it turns out there's some known issues with random field theory that have to be considered when you're doing a power calculation with random field theory. And the first thing is random field theory can be a little bit conservative. And that's okay for inference, because if you're missing activation, fine, as long as you're not adding false positives. But for power calculations, it turns out that random field theory can overestimate the power. So in order to protect against this, Satoru Hayasaka suggests this degree of freedom offset, where he basically takes the original degrees of freedom m and he penalizes them with an offset term, and then uses m prime as the degrees of freedom in the power calculation. So he uses 2 for low smoothness and 1 for high smoothness. He just found through inspection that those worked well. And another weird thing with power calculations and random field theory is that typically as you increase the number of subjects, your power should also increase, right? I mean, that's the whole point. But unfortunately, if you increase your degrees of freedom with random field theory, some of the assumptions of random field theory start to break down, and you can run into cases where power decreases. So in order to get around this, they estimate power in increments of degrees of freedom, and then when they hit that point where things start to go wacky, they use linear extrapolation to obtain the power value. Okay, here are the results. So they did a mock pilot analysis. Basically, they had a data set, I think, with about 40 or 50 subjects, and they used 5 of those subjects to do the power calculation, and then they randomly selected subjects to do an analysis. So over here, we have the effect size in terms of the Cohen's d. That's just the delta divided by sigma. That's what the Cohen's d is. And you can see that the effect is stronger in these red areas, and it's weaker in the blue areas. And then for this one, they selected a sample size of 15, and this is just a power map. So the power is higher where the effect size was larger. It's easier to detect big effects than small effects. And then you can also look at sample size maps. So these are sample sizes for achieving 80% power. And he's highlighting these regions here where approximately 13 subjects are needed for 80% power to detect activation in those regions. So then the last image is the analysis with 15 subjects. And you can see these regions that we were told were powered do show activation. I don't know what happened to that one, but I'm sure there's some, I tried finding the paper, but I'm sure I missed it. Right, so that's the random field theory. The nice thing about the random field theory approach is that my RI approach you can go through and calculate the Cohen's d measure and just plug that into the random field theory approach. And it's actually something where Satoru and I are going to do, is we're going to merge our 2 methods. Okay, next is a false discovery rate based power calculation, which is another whole brain approach. And that uses false discovery rate. It doesn't use alpha. Instead, it uses this false discovery rate parameter Q, which is the average false discovery proportion, or the proportion of voxels that were falsely rejected. So this is different than family-wise error rate, because family-wise error rate is controlling the probability of having any false positive. And now we're just focusing on the voxels that were falsely rejected, and looking at the voxels that were rejected and look at the proportion that were falsely rejected. Not to confuse it with alpha, but typically in fMRI they use a value of 0.05 for Q, but alpha and Q are not the same thing. But Q is actually a function of alpha, and then also this parameter theta, which is the proportion of true positives. And this is some new work by Suckling and others, and it's impressive human brain mapping. So back to our 4 things. Sample size, delta, sigma, those are all the same. But now instead of, we don't specify alpha directly. Instead, we specify Q, our FDR parameter, and we specify theta, which is the proportion of voxels that are true positives. And then we can solve that for alpha and find the corresponding alpha. And then just threshold using that. So here's the maps from that. So in this case, they're looking at what happens as you change theta. So here theta is 0.05, and that's the proportion of voxels that you think are truly active. And as that increases, this goes from 0.05 to 0.25. I have a hard time seeing much difference between the power maps or the minimum effect size, but if you do look at the minimum sample size requirement for 80% power, you can see that the sample size decreases as theta increases, and that makes sense because if more voxels are active, it'll be easier to detect them. So this is a relatively simple approach. You specify those 2 parameters, get your alpha, and plug it into the power calculation. This is just focusing on 3 different regions, and what I think is nice to see is that if you do misspecify theta, that the minimum effect size doesn't change too much. So it doesn't have too much impact on your power. It does have some. OK, so those are all the recent methods that have come out. And I'm now going to talk about something that I'm working on now. It's kind of a newer idea. And that's this idea of internal pilot studies that I mentioned earlier. And it answers the question, how many more subjects do we need? And as I said before, we're using pilot data to update our power calculation. But then the nice thing is we're reusing our pilot data in the final analysis. And it sounds great, but of course there's no free lunch. And we have to pay a price for that. And that's that we introduce a little bias when we do it. So just to reiterate, the problem that you can run into with power calculations is that we're guessing often. We're making an educated guess at what the variance is going to be. And sometimes our guess can be wrong. So this graph is illustrating power is the blue curve, and this green curve corresponds to this axis, which is the % change in cost. And the x-axis, I'm looking at my initial guess in the variance. So this is what I guess my variance to be in my power analysis versus the true, which in real life you wouldn't know, but this is simulated data. So if your guess is right on the money, that would be at 1. You can see your cost is what it should be. There's no increase in cost than what you would spend if you knew the truth. And the power is also right on the money at 90%. So for this, I powered everything at 90%. If your initial variance guess is too small, you're going to be underpowered, which means you're not spending enough money on your study. And on the other hand, if you're like, oh, I'll just pick a really big variance and use that for my power calculation, well then, yeah, you do have enough power, but you're also spending a lot more money on your study than you need to. So the idea is, why don't we just use the first few subjects to run a power analysis and reuse those subjects in the final analysis? Well, what happens is typically your sample size is a fixed value. But as soon as you're treating that as this random value that you're estimating, you can no longer treat it as a fixed thing, or else you'll be introducing bias into your final analysis, which is not good. So I'm going to look at that bias, basically. So here's what we need in this case. For our n, we estimate first our n initial. So I'm calling that power calculation we do before we even collected data. You still have to do that. That's the trick with this, is you can't come to me, be like, oh, I collected 10 subjects. How many more do I need? It's like, where were you before you did the study? Because we need to do an initial power calculation. So anyway, you need to do that initial power calculation and get the initial sample size estimate. And then you're going to update that using the pilot data. So there are 2 sample sizes involved, and then there are 2 variances. The variance that you guess initially and the one that you get with your pilot data. Delta must be fixed. You can't re-estimate delta as well, because then you're pretty much carrying out a hypothesis test on your data, and different techniques must be used to control your type 1 error rate in that case. So I'm only allowed to look at the variance. Okay, so the first step, you run your initial power analysis, and you do this prior to collecting your data, and you get your sigma initial and your n initial. And then it's also important that you set your proportion of n initial that will be used in the pilot study. So you say 50%. And in my simulations, I use 50%, but you have to set that ahead of time. Otherwise, if you're looking at your data and then you pick it, you're biasing your result. The second step, you gather that data, you update your variance estimate, and only the variance estimate. And then there are 2 approaches to determining the final sample size. One is restricted. And in this case, your final sample size cannot be smaller than your initial guess. That's not very appealing, because we want to save money, right? So this is saying, well, you can only spend more money than you initially thought you were going to spend. But then there's the unrestricted design, where you can either increase or decrease the final sample size from your initial guess. So this is more appealing. But again, no free lunch. There's more bias involved with this unrestricted design. And then you just complete your study. So as an example, if your initial power analysis found that you needed 20 subjects, you would run a pilot with 10 of those subjects, if you set your proportion at 50%, and then calculate your power with the pilot of 10 subjects using the updated variance. And in scenario A, let's say your new power analysis said you needed 15 subjects. With the restricted design, your final sample size is still 20. We can't decrease it. With the unrestricted design, you would then set your final sample size at 15, and you would collect 5 more subjects to complete your study. In the second scenario, say your new power analysis says you need 30 subjects, then in both cases you would have to collect 20 more subjects for your study. Okay, so one thing I found is that somebody, Miller in 2005, developed a bias correction for the final statistic that you're calculating to take care of this problem. But he looked at, these are for clinical trials, and those are huge data sets. In fMRI, we typically, like 50 is a huge data set. So I really wanted to look at this for smaller data sets, like what we would see in fMRI. And also, he only looked at type 1 error rate, the impact on that. I also wanted to see how it impacted power. And there's one more thing. I can't think of it now. OK. So here's what I got. This is first focusing on type 1 error rate. This is for a 2-sample t-test. As I said, my pilot was always 50% of my initial guess. This is the true variance. This is what the true sample size should be, 24 per group. So this is for 48. I did run this for smaller sample sizes as well. And they look roughly similar, but I'll tell you what the differences are. OK, so first let's focus, because there's a lot going on here. The x-axis is similar to the one I showed before. It's the ratio of the initial guess to the truth. So 1 means you're right on the money. To the left of 1 means your initial guess was too small. And to the right of 1 means your initial guess was too big. OK, so the solid lines are, and the goal is this black dotted line here. That's 5% for the type 1 error rate. So the solid lines are corresponding to the unrestricted designs. The red is uncorrected, and the blue is corrected. And that's referring to the bias correction. So you can see with the, I should start with the restricted. Sorry. So let's look at the restricted first. So the dotted lines are the 2 restricted cases. So you can see that in this first case, the type 1 error rates preserve pretty well, especially when you overestimate your initial variance. And if anything, it's a little conservative, which again is OK. With the bias correction, the restricted method is the type 1 error rate's actually too small, which isn't good. The solid lines, the red is unrestricted, uncorrected. And you can see the type 1 error rate's very high, which again isn't good. But with the bias correction, what's interesting is that the approach that's more appealing, this unrestricted approach where you can have your final sample size go up or down, you can get similar results as the restricted design that's uncorrected. And more so, I mean, this is a case where maybe we could guess a little higher for our initial guess for the standard deviation and use this unrestricted approach. I know there's a good chance that your type 1 error rate is protected, or there are other things you can do to use these graphs to correct your type 1 error at the end. I also looked at power, and you can see the two dotted lines for when your initial variance guess is too big. You run into that problem where you're spending too much money, your study is overpowered, and that's because you're not allowed to bump your sample size down. You have to stick with your initial guess. Whereas with the unrestricted designs, although power is underestimated here for all the methods, power is closer to our goal, which was 90% up here. The important point is, if we weren't to do a power analysis, this would probably be much worse. Or if we only did the initial power analysis and didn't update it, even though I'm 10% below what my goal for power was, it'd be much worse if I didn't do the pilot study. Last is sample size. The solid black line is the size of the pilot. And then you can see the solid green line is the unrestricted, and it's always right on the money at 24. Whereas, of course, we have too many subjects with the restricted design. So just to summarize that, the bias-corrected unrestricted method, we can control the type 1 error rate, and there's some loss in power. And I didn't show this, but the type 1 error rate, if you increase the sample size more and more and more, the type 1 error rate gets better and better, to the point where you don't need a bias correction at all. And the bias and power decreases a little with larger sample sizes, but especially not as quickly as the type 1 error rate. Okay, I just wanted to overview the methods that do exist now and just do a quick comparison of the three of them. So first was the ROI approach, which was nice because it's fast and flexible, but it's not whole brain. Another nice thing is there's currently software that you can calculate power just by changing the number of subjects. So I haven't built into it yet the ability to change numbers of runs and the lengths of runs. The random field theory approach is nice because it's whole brain, family-wise error corrected. The con with that is in order to calculate the area under the alternative distribution, complicated integrals have to be evaluated, and iterative algorithms are necessary for that. And so it's kind of slow, but I do know that he's working on that right now, and it will become quicker. And the degree of freedom issue is sort of ad hoc, subtracting 2 or subtracting 1, but I'm sure they'll look into that more. And there is software being developed for this, and as I said, we're actually going to combine our two software packages so you can pretty much do whatever power calculation you want. And then there's this FDR method. It's nice because it's FDR corrected and it's pretty fast and easy to do. The only drawback is FDR was recently under criticism in this Chumley and Friston paper that came out this year. So it's not certain how many people are going to keep using FDR as a method for thresholding their statistics. But that doesn't mean there's anything wrong with this power calculation approach. As long as it matches the method you're using to analyze your data, it's fine. Just there's only problems with possibly how you're analyzing your data. So that's it. There's no excuse. I think even rudimentary power, everybody must know a statistician where they're at. And you can give them a little bit of data. You can just average the mean. You could probably give them a t-statistic if it were a one-sample t-test, and a statistician should be able to turn that into a power calculation for you that's at least a step in the right direction. It's better than using rules of thumb or what your friend did. And also, there's software currently available, and there's going to be better software on the way, but people should definitely be doing more power calculations. That's it.
Thanks very much. So we'll have some questions from specifically for this talk, and then we'll generalize. So I see two hands up, starting.
Yeah, just a quick question. Can you give an intuitive feel for the bias correction? Because I'm wondering about the scenario where, let's say you do this internal pilot thing, and then you collect all the data, and then you just give it to somebody else. They haven't been part of this process at all. They just get the data.
Right.
They're not doing any double dipping, and so it would just seem that I don't see how how they would be biased.
It would still come out in, still comes out in the statistics though, because in the simulations, it doesn't matter if I move that data to another computer, I still get the same statistics.
Yeah, but just in terms of intuitively, like if you just give me some data and I have no idea how you calculated the number of subjects, then I do the analysis and I'm not biased in any way. So I'm just
The bias comes from reusing the data.
But I haven't.
It doesn't matter who reuses it. Is that not correct? The bias comes because you're updating your parameters to estimate power from data that's going to belong to the final sample. What you say would be absolutely true if you did a pilot study and then threw the data away to do the main study. It wouldn't matter who was doing it.
I see. So you're saying the number
That's where the bias comes from, is that right?
Yeah, and you just wouldn't know it was biased, but it would be.
Yeah.
Okay, because you're saying, but that's why as you go to a higher number of subjects, it actually doesn't matter.
Right, right, and that's what they've shown in
So
this.
you're saying, like, if you had 2 subjects and you could show an effect, then the bias would become because someone said you had to go to 4.
It's an extremely subtle form of double dipping.
Yeah.
Marla.
Yes, so I come from a psychology background as well, and I was very puzzled when I came into the fMRI and there was no power analysis. But then I realized, obviously a lot less sophisticated than this, is that if you design an experiment with the goal of mind of reducing your beta, which is rejecting or accepting the null hypothesis where it should be rejected.
Wait, accepting the null. Okay.
Yeah, accepting the null where it should be rejected, so a beta error. And given that power is 1 minus beta, then you're increasing your power anyways. But a badly designed experiment, it doesn't matter if you run power analysis and let's say it says that you have to run 50 subjects, it's a badly designed experiment anyways.
Oh, I see. So you're detecting something, but it's kind of meaningless?
Yes.
Yeah, that's up to the psychologist. Like, they need to make sure. I guess that's where I'm off the hook, right? People give me data, I run the calculation and give it back. And it's also really important that don't do your power calculation 2 weeks before your grant's due. Every time I do a power calculation, they need 4 times more subjects than they thought they needed. Well, not always that bad, but it happens really often. And then you have to rethink what regions you think are interesting.
What was the criticism by Friston of FDR?
Oh, I'm trying to remember. It has to do with the fact that with FDR, you assume that there are null voxels. But in reality, what?
I didn't hear what you said.
Oh, that there are voxels in the brain that aren't doing anything. But in reality, all the voxels are doing something. So it breaks some assumptions of FDR that you have things that are active and not active.
It's also criticized because it doesn't know anything about space. So it doesn't make any assumptions about proximity or clustering or anything. So they just got in SPM8 now. There is a new version of FDR, which is based on cluster extent size rather than on the proportion of voxels that are active. It's based on the size of the cluster of active voxels, and that tries to get around that criticism, I believe. But I don't know how you would use that for a power calculation.
Yeah, this FDR thing definitely wouldn't work for it.
Nicole.
No, just as a comment about this last point, we're actually starting to work on Bayesian spatial temporal ways of using the spatial information to adjust FDR spatially.
Yeah, I think that's really
initial work, but we're thinking about
so
it.
that's, I think the Chambly criticism is it's basically it doesn't pay any attention to what we know about how the brain works. So just one point about grant proposals. I'm on a study section right now, and we see large numbers of fMRI proposals. If there's one thing that's worse than not putting a power calculation in, it's putting in one that's clearly garbage. And what's astounding is how many people are paying lip service to the idea that you need to have a power analysis. And the Desmond and the Glover and Desmond paper has become almost like a dogma that you have to have a little section that says we're going to run 20 subjects in each of our experiments because that's what gives you 80% power in a fMRI. And of course it's nonsense, as you rightly pointed So I think you're absolutely right. The future in fMRI studies is going to be where subject size is determined, sample size is determined by power calculations. But it's going to be really important that people writing grants take that seriously. Don't think they can get away with just paying lip service to the idea.
Yeah.
It causes amusement on study sections when you see these little paragraphs at the beginning of the general method section, which clearly the person is very anxious to demonstrate they know about power, but not anxious enough that they've gone out and found out how to do it. So I'm just reiterating your point. I think your services will be in greater demand.
So I need to get
Personally, I want to get your email address.
So I need to get the software done so people don't email me asking me to do their power calculations.
Yeah. But I just want to raise one important point, then we need to go into general discussion, which is one thing that you did, because you talked about number of runs or number of observations per run. But because that is not really what you want to know. What you want to know is the efficiency of the parameter estimate at the single subject level. So if I have two different ways of estimating a parameter estimate that captures the experimental contrast that I'm interested in, and one of those is efficient, one of those is inefficient, then I'm going to need a longer run in one case than I am in the other.
And that would come out in this too.
I appreciate that. What I was going to ask though is there anything at the moment that allows people to adjust for that?
For efficiency?
Yes.
In terms of power, or
So
just in terms of just comparing efficiencies across?
Well, I'm thinking, suppose if
Different
people use a
paradigms.
finite impulse response method, for example, to estimate, that's inefficient compared to using something like a canonical hemodynamic response, just to get a parameter estimate that says this is what the difference is between my two conditions. Is there anything in the power calculations at the moment that allows one to factor that in, and then to determine the number of trials that you need or the number of runs that you need?
As long as you could build it into your model, you can do it.
Right, it's kind of captured by the variance of the data that go into, right? Because the variance estimate will be higher, because the model for the for the power analysis has to be the same one you're going to analyze with. So the variance will be higher for those parameters using the FIR model.
Well, the residual variance or the variance based on the model? It'd mostly be coming from the model variance, right?
Right, but the variance estimate that goes into your power calculation is the combination of those, right?
Right.
But that itself is a mixed variance. That's the parameter estimate itself contains, as you know, different sources of variance, so it's kind of complicated to do.
No, Russ is right. It's better to have data that most closely represent what you're doing the power calculation for.
So let's go back to step back a bit and have a general discussion. So we had 3 papers this morning. We've had two papers that are really concerned essentially with making accurate inferences. That is, given a particular experimental question, figuring out how to analyze your data in such a way that you get as near to the truth, whatever that might be, as there might be. So Chris was emphasizing the fact that it's not really a great idea to analyze your data in one way and then to analyze it in another way, which is essentially a reanalysis of the original data. And I think people become sensitive to that, not least because of the paper that you published in Nature Neuroscience. I think double dipping is referees are very common now. I've noticed very prone to say double dipping all the time, speaking as a recipient of this criticism. And then Jeanette was pointing out something which I think is really important, and it's something that we emphasize all the time. Our discussion sections are getting increasingly long on this section, which is that null effects in a functional imaging study don't mean a thing if you don't have some kind of notion about what the predicted effect size was, and therefore what the power of your experiment was to pick up that effect. And I think you're formalizing something that I think is really important, which is affirming the null hypothesis, or drawing strong conclusions on the basis of a null hypothesis is a pretty worthless enterprise, particularly in our field, which, like psychology generally, actually, it's interesting. A lot of the issues that we've been talking about are not issues specific to functional imaging. They come out in behavioral science generally. Psychology experiments have been criticized for many years for being underpowered. The average cognitive psychology experiment is underpowered, and people have pointed this out many, many times. particularly true with functional imaging, particularly when you have to control for false positives in some way or another. So null effects generally don't mean a whole lot, and it's not a good idea to design an experiment which predicts a null effect and then to draw a strong theoretical conclusion on it without really knowing what the underlying power is. And I think that's equally important as opposed to failing to find effects. And then Russ was pointing out that one can go beyond that kind of a traditional Fisher type approach as applied to statistical parametric maps, which is what both of these talks were essentially about, to ask a rather different kind of question, which I think is a very bottom-up, essentially a very bottom-up form of analysis, which simply says, what does the data tell us if we put it through these kinds of algorithms and the like? And in fact, what was telling about your analysis was just the size from an fMRI point of view. This was an enormous amount of data, which I assume is likely why you were able to get such beautiful results. So that was a rather different approach. So I guess one question is, one can ask, what are the circumstances under which these different kinds of analysis approaches are most appropriate? Both Jeanette and Chris were really focusing on a kind of quite traditional approach that's been around in functional imaging since the get-go. And I think what you were saying, Russ, was that approach can only take you so far, particularly if you want to make inferences on the basis of the data about what the underlying mental operations might have been in the subjects who contributed to the data. So I guess one place where we could start is, what are the right circumstances for a priori thinking I'm going to use one approach rather than another? More generally, does it really matter? Can you collect the data and then decide on what you're going to do afterwards, or use the same data to do different things for different purposes? Don't know if people want to weigh in on that.
Sure. I think it's actually it's an interesting open question that has been raised particularly by all the circularity stuff. Of one of the concerns that I have about even though I think that bringing those issues to the fore is great, one of the concerns I have is that it forces people into this idea that you have your data, you have one hypothesis, you test that hypothesis, and then you're done with those data, right? And that anything else you go on to do is somehow tainted or cheating, and so it tends to kind of canalize people into saying, I can't try anything different, I can't do any sort of exploration, or at least it kind of stigmatizes that sort of thing. And I think that our field hasn't been around very long. We have this very stylized approach to analyzing our data, which is a tiny part of the model space that one could work in, and the worry is that this kind of that one of the ways that people take these concerns is to drive them towards this very kind of focused, one hypothesis per data set sort of thing. I don't know what because obviously you do want to penalize the results that come out of data, data mining in the sort of the bad sense. But how you do that without sort of stigmatizing sort of exploration is a question that I haven't been able to get my head around. I don't know if you have thoughts.
Yeah, I share your views, Russell, maybe exponentiated. It seems to me that, although there wasn't, the topics here weren't really about multiple hypotheses tested on the same data, but the aversion to that seems to be anti-scientific. And it's hard to find good logical arguments for it, and of course, as a matter of review of historical practice, it would be utterly disastrous. People had been forbidden to test multiple hypotheses on the same data. We would not have the Copernican theory or Kepler's theory, or the atomic theory, and one could go on and on and on, all of which were produced by data dredging.
I guess the difference is between heuristic and confirmatory analysis. So, I sat on another committee when I was in Britain that was dominated by epidemiologists. And if there's one thing that really upsets an epidemiologist, it's setting up a study to address one question and then adding other endpoints.
Yes,
The
unfortunately.
famous multiple endpoint criticism. And this kind of echoes around that if you're going to do that, you have to go back and redesign the study, because now the argument is your original, everything that you supposed in the first place has to be reconsidered in the light of these other endpoints that you're going to have, because you've increased your type 1 error, etc. It seems to me the critical question is whether you're analysing a data set for heuristic hypothesis generating reasons or for confirmatory reasons. It seems totally appropriate to design an experiment to answer one question in a confirmatory way and then to mine those data to generate hypotheses which you will go on to test. So that seems to be a good compromise.
I think it's an unfortunate and unsustainable distinction except in special cases. So here's a well-formed issue over a class of problems. What is the reliability of a particular inference procedure? That seems to me the appropriate question. If in fact you know a search procedure has a certain reliability over the class of problems to which you're applying it, then I don't see the distinction between confirmation and heuristics or is tenable. If the very fact that the procedure is reliable is confirmation of its results.
This I think will, I'm sorry, I don't want to, let me just say one thing, will make us problem sound, but I think one has to distinguish between reliability and inference with respect to the subjects from which you collected the data and the generalizability of that data to the population that you want to generalize to. So you're absolutely right, the thing can be absolutely reliable for the subjects that you've sampled, but that doesn't guarantee that you've got the, because of the way you sampled those subjects and the possibility of bias and noise and whatever, I think you can have something that's super reliable for your subjects that doesn't necessarily generalize to the population.
Well, of course.
Of
course, that's
a
not.
good example of that is what used to be done in fMRI. The reason we used to have 6 and 8 subjects in fMRI experiments was we used fixed effects statistical models. These produced p levels that were unbelievably low. P to 10 to the minus 9. The problem was the effects never generalized to the next 6 subjects that you ran. And the reason, one of the major reasons why there was this big shift from ends of less than 10 to ends of 20 or more was the realization that one had to use something like a random effects model to gain the inferential power that allowed one to generalize to subjects other than the ones that you just run. And I think, so just the issue of reliability in itself is not sufficient. You can have a really reliable, solid result in your subject sample, but you don't necessarily have the inferential power that's needed to say that's what exists in the population.
I think your response changes the topic to an issue where there isn't one in dispute. The question is whether you have sampled correctly or by whatever standards, and now you want to search for multiple hypotheses by a search procedure that, given the representativeness of the data, you know to be reliable. You want to call that heuristic and make it second class. I say it's first class, and depends how good its class is, depends on the reliability of the search procedure, and you can test that. Sometimes you can characterize it analytically.
Anyone else want to weigh in? Chris?
I mean, well, I think some of the things you said, some of the things that Mick said is kind of what I would say as well. I think that the other way of thinking about it is hypothesis generation versus hypothesis testing. I think you have to be careful that you're not using the same observations to generate a hypothesis and then test it.
So, no, you don't. I mean, obviously, you know,
I'd like to be a bit more controversial with
you can drag out all kinds of horror stories where people make terrible mistakes. On the other hand, if you make a general principle, I will show at least the one you purport to. I'll make a straw man of you. Yes, the very strongest version, as in don't do multiple hypothesis testing on the same data. You will wipe out the history of science. So it seems to me this is really a very logically complicated issue, and it doesn't do any good to pull out, here's a worst case, there's a worst case, nor does it do any good to have what seem to me slogans. This is exploration, this is confirmation, this is heuristics, this is not heuristic. I mean, sometimes you have proofs about reliability, yeah? Under assumptions, always under assumptions. Sometimes the assumptions aren't met. Sometimes you don't have proofs, that's when I say you got heuristics. But it isn't a question of researching.
So, how much of this matters with these new methods of machine learning and the like? So one thing, for example, that's done within the pattern classification procedure, it is anathema to use the same data to generate your classifier as it is to then use it. And so that's an example where there is a very rigid separation drawn between, if you like, the generation of the analytic tool and then the use of that tool.
And it actually seems to be that you can think of this issue of the fixed effects thing as the same kind of overfitting issue that people there are trying to worry about, right? It's
Yes,
you're right. If you had a method that didn't overfit, then it would be fine to do your things with a fixed effects model, right?
Exactly. So what we've done a little bit with pattern classification ourselves and found that it raised a lot of interesting new questions about, for example, how you determine the reliability or the significance of the effect in a way that can be communicated so that other people understand what we mean by statistically.
Right. So I mean, the approach that we've taken, and these other people who work in this area can speak to it, is to do randomization stuff where we always take the data, randomize the labels, do it 1,000 times, get a p-value out of that, and that seems to me to be the cleanest way.
That's exactly what we've been doing as well. We
So
just
that's
randomize.
the general, it's a permutation approach.
I think, that goes with having, I think one thing that we try to do to students often is whenever they come in with a good result, to assume that it's bad.
Right.
And this is kind of this is a pervading mindset among machine learning people. You don't believe good results. And so the easiest way to test them is to actually randomize the labels, as Russ was saying. And sadly, most of the time, the skepticism is warranted.
So I guess my point would be those sorts of tests, permutation, which we did as well, I recall.
Yeah.
Yeah. Those sorts of tests work to tell you whether the conclusions that you're drawing with respect to the data set that you've currently got in front of you are valid. How do those tests allow you to generalize to the population?
Well, that always depends on your sampling procedure. Right? I mean, there's nothing internal to the data unless you know externally about the external population. It's going to tell you whether it's representative, let alone random.
But that's not true.
You
But-
have to know how.
Right. I mean, you can think about doing leave one subject out, right, rather than and see to what degree can you predict new people rather than within people.
So the irony of all this is that some of you will remember when the first PET studies came out from Wash U, the standard method was to split the data into two halves and to generate a set of regions of interest and essentially, if you like, hypotheses, as I call them, on one half of your data and then to confirm them on the other half. That was the original method that was used by Mark Rabel and colleagues to do the first demonstrations that brain imaging was sensitive to cognitive processes. That seems to, it's very expensive, particularly with PET, it's phenomenally expensive. It was kind of double the number of subjects, but it seemed that kind of somehow fizzled out very early on.
Well, because it's so expensive.
Yeah.
And the other kinds of resampling schemes are less expensive for data, and you have asymptotic results about their behavior. On the other hand, you're basically testing for internal coherence of the kind within your sample. You can.
If you have a sample, to my shame, I published PET papers with 5 and 6 subjects in them, along with everyone else at the time. I think you may have done that.
No.
What was your
I published fMRI papers with 8 people, but that's my worst sin.
That's your, you never did a PET.
No.
So you're under enormous pressure with that to have small n's because of the irradiation of the
But
inside.
the point is, these procedures don't guarantee against your having an anomalous sample over the population to which you want to generalize. Again, you just have to know how you obtain your sample.
Anyone else want to weigh in on that?
Well, maybe to just tag along with that. So one thing that we tend to do is actually, if you're doing things like leaving one subject out, take your data matrices, plot all of them on the same scale. And sometimes you notice that the scanner was doing something odd one day. If you were actually going to put subjects from that day together with subjects from another day, your classifier would be led astray because, say, the mean for what a voxel or an area is doing would be different from one day to another. And it's very easy for that sort of thing to happen. Or even within one subject, one run might be substantially different from the others. And the only way that you can deal with that is to actually just make plots of data. You don't need to look at labels, but that's actually it's part of ensuring that the distribution is roughly the same, because that's really the basic assumption for all the learning methods.
We've actually found ICA to be really useful. So you do a group ICA with all of your subjects and runs, and then look for components that are basically loaded by a single subject. And often then you can go back and look and see it's all motion or something funny like that.
Yeah, I mean, standard outliers is just fiddling with your data set. It's doing the prohibited procedure.
But of course,
God knows how many papers do it in secret.
in principle, of course, outlier detection in principle is a good thing. When you've got a complicated multi-dimensional data set like fMRI, outlier detection is not quite so straightforward. Either defining it or finding it is a little bit more difficult, particularly in raw data.
But that gets at the importance of what Russ was saying. So you want a measure that has nothing to do with the labels.
Yeah. So I wanted to go back to one of Chris's slides where I managed to prevent myself from projecting at the time, which is where you have data in blue and results in blue, and then assumptions in red. And what you want is those assumptions in red not to colour the blue line. So, in other words, that there's somehow some connection between data and results, which is independent of or should be coloured by your assumptions. But essentially, any statistical model is essentially colouring the data to produce results as a function of assumptions. And that's most obvious, of course, in a Bayesian approach, where the results are completely determined by how you conditionalize your data in terms of estimations of prior probabilities and the like. So I guess the more general point is it seemed to me that was a slightly, perhaps inaccurate, slightly inaccurate depiction of what goes on.
I think you should be careful not to read too much into the cartoon.
Okay.
Right, because it kind of suggests that you can do science in a way where the results are not theory laden,
So I
which
thought
is
that was
simply
perhaps-
not true.
I think it's that the idea is your assumptions are already picking up on parts of the data. I mean, you're doing something, but you don't want it to. You don't want fundamentally the assumptions to drive everything that's going on. And there is this, I put it as being no interaction versus complete dependence, and it's always going to be somewhere in between. It's a matter of how
Well,
far
I guess
in
the
between.
point I'm making is that there is no means of getting from A to B without the red box.
Right. I mean,
except for unless B is just completely restating the data you
Right.
collected at A,
Yeah.
right?
Well, the other point is that if you're using methods that have a regularization term, then you are essentially conditioning your data by some strong notion about the model in such a way that the results are a mixture of what your pre-existing model was and what your data was. That's what regularization is doing, and you can have situations where what you end up with is some kind of a solution where the penalty term, the regularization term, is so great that the data don't play a whole lot of a role in the solution. So that can be allowed to vary as well. It can be allowed to be conditioned by the data. We do this when we're inverting, for example, electromagnetic scalp data to try to figure figure out where the sources are, the regularization term in that can be huge. So I'm not certain about whether, how far you can push that.
I mean, I think it's what we're trying to highlight is that it's like, even in cases where it doesn't seem like you're making huge assumptions, there are assumptions that are built into the data, and we always have to be very, very aware of what those assumptions are. And so in the cases that I'm highlighting here, those assumptions are ones that often don't always appear obvious to people. And the point of that is to say, look, in any analysis there are these assumptions. And you have to understand how those assumptions interact with the data in terms of what you're trying to show. Now, that doesn't mean that you have to have zero interaction, but you have to sort of have a thorough understanding of those assumptions.
Just on a related note, since it's something that hasn't really taken hold in the functional imaging literature, which is really common in other areas of data analysis and statistics, is your sensitivity analysis. So how sensitive is your outcome to the assumptions that you're making? And you can change those and see, do you still get the same inference? Do you still reach the same conclusions? And that also gives you a notion of robustness and reliability and generalizing to the population at large. If you use different analysis paths and you get to the same conclusions, that tells you something.
I think that's a really good point.
Well, you in effect showed a kind of sensitivity analysis, at least one case, where you showed you get the same result with what was a random input. I mean, that seemed to be the most convincing example.
Not necessarily the one that the authors were anticipating. Any other general points?
I was just wondering, so you're not a fan of plotting the data and what's in the regions that are active, but if you're lucky enough to have a significant interaction, I find it's really hard to describe an interaction without doing some sort of averaging over the region to at least describe, for which group it was going up or down versus the other group.
I guess it depends. Like the difficulty is what people read into those plots. I think in themselves those plots contain useful information, but there's inferences that go beyond what you might want to say about it. So you simply want to describe exactly what the shape of that interaction was, but that's not what sort of happens when you're plotting these things. And so I think it's something like in simple case, you can do some people bring up the example and say, I do some contrast. I want to know whether these were activations or deactivations of the baseline. But pure contrast doesn't tell you that, so you want to plot them to show it. But you can just say what they are, right? You don't need to plot it and provide this kind of misleading, what we call sort of like visual inference.
I think science doesn't work very well without being able to summarize and create some kind of a structure that people can grasp so as to understand the nature of the matter. I understand exactly. I don't think there are many people who, maybe some, but there are few people who think when you plot a bar graph of the parameter estimates that have been derived from either a peak voxel, let's say, or a region of interest, and you plot that parameter, those bars, that you're necessarily giving any more information than was present in the original parametric map.
I disagree because of the tendency for people to do subsequent statistics on those.
But
Which happens quite often. And so it's like people clearly are not.
It's a psychological effect. I think, like you were mentioning yesterday, Bill, people get more convinced when they see a picture versus the words. And even if you're trying not to do that, the tendency is going to be to try to attribute.
I think there are two questions here. There are two issues. One of them is if you're depicting your data so as to simply describe it or in a descriptive manner, then I think you have to be very clear that's what you're doing. But there's another thing. So in the case, for example, if the example you gave with 4 levels of a dependent variable, the correct way to determine which regions of the brain are sensitive in some way to those independent variables is a 4-way analysis of variance. Once you've selected the voxels that survive your corrected threshold for that anode, it's perfectly appropriate in some way or other to produce a summary of those data for each of the independent variables, plot it, and to do follow-up contrasts. That's exactly, there's a whole, Weiner didn't write his book for nothing. It's perfectly legitimate. The problem comes when, as you say, you're affirming the original inference.
Right.
But that says that people have to think more carefully about the orthogonality
Absolutely.
of how they identify regions that are sensitive to the experimental variable, and then go in there to interrogate the reasons for the sensitivity. And the
Right.
problem comes is people try to do the two things at the same time.
Right.
Is that fair?
Yeah, no, I think it's fair. I mean, there's definitely, you know, the approach you suggested is one way around these problems.
It's not the only way.
No. But it sort of depends on, it really depends on exactly the field people are in. I think different fields have slightly different ways of approaching the question. I mean, like in the visual system, people have a very much an approach, which is we kind of have this nice sort of idea about regions we might want to look at. So in that 4 contrast design, maybe it's like A and D are faces and objects, for example, because we know there's a region with water faces and objects. B and C may be something else. And so it's kind of like you've got you're trying to pick up a region of interest and then say something within that region. It's not like you're doing a whole brain search. That's kind of one approach. Or it may be that you do want to do a whole brain search and look for areas that do show. I mean, there's different types of questions that people are asking that I think differ across different sort of domains.
The bottom line is you need to be extremely clear on what questions
Absolutely.
are that you're asking.
And
The circumstances where your follow-up question is simply the same question written in a different way.
right. And I think that the disturbing thing, and what I highlighted, you know, in my talk, is that often people do not provide sufficient information for you to understand exactly what they did. And in those cases, it's you know, or just to address this issue, you know, address the issue of the assumptions, at least say something about it, because I think method sections are getting shorter and shorter and are getting pushed into supplementary material. And I think that's actually quite a disturbing thing. I think
I agree with that. So, yeah, go ahead if there are.
No, I was just thinking about what's happened to scientific writing. It is bizarre. I mean, you know, major machine learning conferences, which, yeah, it's all computer scientists. All the papers are online, but there's an 8-page limit. So don't have a complicated theorem. You can't present it. And similarly, various federal agencies have been compressing the length of application. Again, don't have anything too complicated, you can't present it.
Well, as of January the 25th, anyone writing an NIH grant will have 12 pages.
So,
and anyone who's going to spend 4 pages on their fMRI methodology is not going to find themselves giving themselves too much time for.
no, that's right. So basically what you're doing is sort of signaling, sort of waving, hey, send me money.
So one last quick thing to talk about before we break for lunch is, I can't remember who mentioned it, maybe Russ, about the need for databases for fMRI data. And I think it's one of those things that, you know, everyone agrees in principle is absolutely essential, particularly given, I don't know, your $300 base is, I don't know where you stand. That was at the low end.
Per half hour.
That was starting with a half hour.
That was, oh, right. In that case, I think, oh, goodness me. We don't allow people, we charge by the hour. But anyway, it doesn't matter. When it's costing $600 or more a subject, it does, and this is mainly publicly funded research, it does seem almost scandalous that there isn't a public repository of this data. And unlike, for example, in the fields of genetics, where you can't publish a gene sequence without depositing the data in, I think, one standard repository. And it's a really, the reason it hasn't been done is not, I think, because people don't want to do it. It's because it's just so hard.
Well, but there's also an unfortunate history, right? The person who tried to do it did it first. Mike Gazzaniga did it in such a way that he basically ruined it for anybody else who wanted to come do it afterwards, because now everybody viewed, because his data center in theory still exists, even though in reality it doesn't. He did it in such a way that where he tried to force people into doing it and sort of, you know, blew the social engineering. It didn't work, but now he has the mind share, so anybody else who wants to come along, no one's going to give them money, right? Because they say, oh, Gazzaniga's already done that.
And I think it's now widely conceived as a failed enterprise as well. So for people who don't know the history of this, I think it was an NSF grant.
Dana Foundation and NSF, yeah.
That was given to people at Dartmouth with Mike as the PI to generate a public database of fMRI data. And Mike's idea was firstly, anyone submitting functional imaging experiments for the Journal College of Neuroscience, which he was the editor of, would be forced to deposit their data. So you can see what that did to the submission rate for functional imaging data into the JSCN. I should just say by way, just it's worth pointing out that what you had to do to submit your data to that database was harder than it was to write the paper. It was a nightmare to do. It was just the most.
It was like at least 1 person week of work.
It was a nightmare. It was far too hard. But secondly, Mike tried to persuade the editors of headline journals that they shouldn't publish functional imaging data without forcing people to archive. And that went nowhere. In fact, there was a lot of pushback from the organisation in brain mapping and from individual investigators that said that that's not the way to make this work. It's premature. We don't have a good way of either formatting or describing the data. And people hadn't really taken on board the fact that many of the data sets that we have don't mean anything without the subject's behavior going with it. So it's not just a question of archiving a bunch of scans. You need to know the experimental design, and you actually need to have the subject's behavioral responses archived as well. Otherwise, it doesn't make a whole lot of sense. And it just seems to have gone, as you say, for political.
Yeah. I mean, I think there's also a dirty little secret, which is that there are a lot of people in the field who know how to punch buttons on SPM and make pictures and are not comfortable with the fact that someone who actually knows what they're doing could look over their data and figure out, look how this person screwed up. And I think that is a serious feeling that some people have.
This is clearly a federal problem. It applies in a lot of domains, but it seems that there's only one sensible way to solve it, and the sensible way is that NIH, NSF set up a repository. They set up documentation standards, and they require that if you take their money, you put the stuff there. And you know, you shouldn't let the best be the enemy of the good here. It's true that there's a lot of documentation one would like, but even in the worst case, you would like a tag to the papers that use the data.
So I think you're right. I mean, think if NIH took a strong stand on this, like they have done with depositing publications in Biomed, that the problem would be solved overnight. Suddenly everyone will be able to do it. Yeah,
It's amazing how they do it.
But it's still these questions of exactly how, what form of the data should be deposited. I mean, it's tough, right?
That probably would require the work of a well-informed committee for a couple of years to come up with something that would work. But it would be well worth the effort and well worth the cost.
So a group of us met at HBM a couple years ago that included people from FSL, SPM, Peter Fox, a bunch of different people, David Menessen, who were interested in this issue, who kind of all agreed that, you know, that something needs to be done. And I think that the software people, particularly the FSL and SPM people, really want to make it be the case that one day you can click a button and say share this particular data set. And the idea being that you don't necessarily have to share all of the raw data, that, you know, it's certainly good for people to share all the raw data, but sharing things even like statistical maps or something like that would be much more useful than sharing nothing.
Yeah. I think one thing that has been good in the last couple of years is the nifty image format. That means that it's now not that difficult to analyze the same data on multiple analysis platforms. And that's been really, I think, quite helpful. But that's a small step.
So how do you get the federal government to set up such a 2-year committee and put in the money to actually create an alternative to Kazanaga, and the most difficult step, make people receiving the money
Well, they'll comply.
That's the easiest step, right?
They'll comply.
The NIH says.
No, the hardest step is making the ruling in the face of the outrage.
Right.
I think it requires, the push will have to come from the field for that. So I think, you know, things like genetics, it's clearly, it's pointless resequencing a gene that someone else has sequenced. So it's just crazy to do that. And most of that's public money. So that was easily done. But there, it's very, the methods are standardized and the actual information is relatively